there, I'm a student in Dr. Greco's class, Physics 1, and here is problem 3 on test 2. Okay, so the given, what is all the way up here, the length of the copper wire that we're dealing with is 1.9 meters. The area, the cross-sectional area is circular, so we know that the radius is going to be 0.0004 and the cross-sectional area is going to be pi r squared. The mass that we're going to hang on it is 6 kilograms, and the stretch that is going to make this wire go is 0.0019 meters. We're given the density of copper, which is what we're working with in the wrong units that we want, and the molar mass. So the diameter of the copper atom is defined as mass over density raised to the 1/3. Now, I've gone ahead and changed density into usable units that we can actually set under mass and raise the whole thing to 1/3. And here we've got 2.27 times 10 to the negative 10 meters for the diameter of the atom, which is very typical. This 10 to the negative 10, that's how I know we've got to the, at least in the blanket space of the right answer, because that's the typical diameter of the atoms that we are dealing with these Young's modulus problems. The stiffness of the individual spring we're going to calculate here with this equation. We've got to find the Ks of the entire system, the number of series, and the number of chains. So Ks, okay, is just defined as mg over delta L, which I've gone ahead and calculated. Remember, the mg is essentially the force that's acting in the system, which is just gravity, which is mass times gravitational constant 9.81, the acceleration toward the center of the Earth, over the delta L, which we were given up here. Delta L, right? Nope, not that one. That one right there, delta L. And that gives us 3.10 times 10 to the 4th. So that's the constant of the entire spring system. Now we're going to calculate number of series, which is L over diameter of atom. Diameter of atom I just calculated here. L is given to me. And the number of chains, which is the cross-sectional area. Again, we're going to use this pi r squared formula, and over d squared, which is again diameter that I just calculated. Now when I plug and chug all of these numbers into the equation, I get 26.6 as the spring constant, the units, of course, right there. Now Young's modulus. Now excuse on my scratch work here, but the Young's modulus is essentially a variation problem, right? So they've changed up the thickness on us, right? Instead of 0.0004 as the radius, they now have 0.0008. Now that's fine. And they change up the length, which is 3L equals 3 times 1.9 meters. Now, Young's modulus, because it is a property of the actual wire itself, it's not going to change, right? However, say the length and the thickness might. So when I calculate Young's modulus, I'm just going to go ahead and put in the old values, right? Force is mg, cross-sectional area calculated pi r squared by this r, 0.0004. The length is still 1.9, it hasn't varied, I haven't varied yet, and the delta L, which they give up at the top, is 0.0019. Now when I put all these numbers in and I plug and chug, I get 1.17 times 10 to the 11th, which is an innate property of the actual copper wire. Now when I actually sub in the correct values of this problem, right, 0.0008 because it's 2 times the radius, and then 3 times 1.9 because it's 3 times the length, I get that the delta L, or the stretch, is 1.5 times 10 to the negative 3 meters. Again, this is Caroline Wu for the test wrapper. This is problem 3 on test 2.